So far, we've assumed that the mobile application always had to be connected to the server in order to work, accessing the REST services, and through them the database hosted on the server. However, GeneXus allows us to create mobile applications that can work partially connected or even completely disconnected from the web server. Next, we will study each case. Let's review the concepts related to connected applications. Online applications are those that must always be connected to the internet in order to retrieve data and work with it. When the device is offline, the app will only be able to work with cached data, but will not be able to browse new screens or update the data. Once compiled and installed on the device, the application needs to access the web server's service layer in order to run the data providers that return the data and the business components that run CRUD operations over the database. The data cannot be obtained without an internet connection, because there isn't a local database and all the data is on the server. What happens if we tap to see the data from the database in an online application? By tapping on the device, for example, on the Sessions icon in the menu, the Work with Sessions component is invoked. The corresponding code is run on the device. In its internal logic, this Work with component calls the server to have it return the data to load in the fixed part of the Work with component through a REST service. Then, it asks the server to run another REST service which returns the grid data. With the data returned in two responses, the screen built, the fixed part on one side, and the grid on the other. In this architecture of an online application, the REST services, the data providers that access the data, and the database are in the server, so they can only be accessed through an internet connection. Now let's see the case of partially connected applications. It may happen that part of the application keeps running when it's disconnected from the internet, while the other part must stay connected in order to work. It may even happen that we're not interested in running the app synchronization because we want to be completely independent from the data on the server. Everything would be managed from the device, as the app installed on it wouldn't communicate with the server. Another particular case is when we want the device to be able to receive the changes made on the centralized database, but never to send its own changes, which will be saved in its local database. These applications that can work without an internet connection are called offline applications. Let's begin by talking about offline applications. In this case, we want all the data managed by the mobile application to be accessible even when there is no internet connection. Lastly, we will examine a mixed case in which part of the data can continue to be managed exclusively in a centralized manner. Here, the entire structure of the centralized database on the server that is managed by the mobile application is mirrored on the device. That is to say, an SQLite local database will be created on the device with the same tables. However, replicating the entire dataset of the centralized database is not mandatory. Instead, a subset of this data can be sent to the device database. That is to say, not all the data stored in the server has to be sent to the device database. Certain filters can be defined and have only some of the data or some of the tables saved in the server database sent to be effectively stored in the device. In offline applications, in addition to a local database, all the programs, data providers, and business components used to obtain information from the central database are required. Now, they should be programmed in languages of smart device platforms so that they can access the local database. From now on, regardless if there's an internet connection available, the application will always work on the local database. The device app will access the server only to synchronize the data of both databases. The entire services layer that was stored in the web server, and which contained the data providers to retrieve the data, and the business components to update the data saved in the tables, will now be in the device. They are implemented using the platform's language to access the local database and compiled in the binary file. In this way, all CRUD operations will always be performed on the local database. They will never be run on the server database. The application will contact the server only to synchronize. When the connection is restored, the databases have to be synchronized. That is to say, send and receive the changes to and from the device. This synchronization will always be started from the device, because the server cannot know when the device is connected. The information locally stored can be synchronized with the data on the server. This is optional. Remember that we may never synchronize or do so on demand. The process through which the data changed in the device is sent to the server is called send. Also, the data on the server that has changed is sent to the device to be updated at regular intervals or on demand. The process through which the data changed in the server is sent to the device is called receive. The device and the server communicate through REST services for synchronization. Both send and receive operations are implemented with server-side and with client-side logic. The objective is to have the client run the least processing possible because it has much less power than the server. When the device starts the send operation, which can be started manually when the connection is restored through the synchronization.send method or never, it must have built an ordered list of the insert, update, and delete operations performed since the last synchronization. That is to say, a list of operations in pending status. This list is sent to the process on the server. It must run through this list in order and execute the corresponding operations over the database, returning the result to the client side. Remember that regardless if there's an internet connection available, the device will always work on the local database. It will only access the server for synchronization. All changes made over the local database are saved as synchronization events in a table called GX pending events. This table stores in an ordered manner all the operations executed using business components. The details stored include the name of the business component where the operation was executed, the business component JSON containing the event's data, the type of operation made, addition, deletion, or modification, and its status. Every time the device runs a business component, the event is stored and is left in pending synchronization status. When the send operation is started, the client translates the list of all the events with pending status into an SDT and sends it to the server. In the server, the procedure GX offline event replicator is programmed to read the SDT and run CRUD tasks in the order of operations coming in the SDT JSON. The GX offline event replicator procedure can call other auxiliary procedures to address synchronization errors. When the device needs to receive the data changed in the server, the receive process is started. The synchronization's behavior is configured using the properties of the offline database object. In particular, the data receive criteria property that determines when the synchronization will be made to receive data. The synchronization's result, that is to say, the data left in the device, is independent from the configuration selected because it determines how the data is sent, not what data is sent. This is determined according to the filters set in the offline database object. The synchronization that enables the device to receive data from the server can be made with a certain granularity, by table or by row. When this granularity is set by table, all the tables changed since the last synchronization are sent to the device. When it's set by row, only those records changed in each table since the last synchronization are sent to the device. Synchronization by table is useful in scenarios with a small number of records, or when changes are made very frequently, because in this case, almost all the data has to be sent in every synchronization. Its advantage compared to synchronization by row is that it requires significantly less processing on the server side. To determine which tables were changed and therefore have to be sent to the device, A hash that identifies the data set of each table is used. When a client requests a synchronization, it sends the hashes of each table to the server. They were sent by the server in the previous synchronization. For each table, the server calculates a new hash with the current data after applying the filters set in this device, and only sends the table's data when the new hash is different from the previous one. That is to say, only the data from tables that were changed are sent. If the table wasn't changed since the last synchronization, for this table no action is performed. Messages are sent in JSON format. In the first synchronization, there is no data in the local database, so all the data in all the tables is sent. Note that this doesn't mean sending all the data stored in the server, because data can have filters defined in the offline database object, as we've said before. In addition to saving the data in the tables, the hashes of each table are stored. In future synchronizations, the device sends the hashes received, and the server sends only the data of the tables that were changed. When they are received, the entire content of each table is deleted and replaced with the new content received. Synchronization by row only sends those records that were changed since the last synchronization to the device. So first, it determines whether the table has changed or not. To determine which tables were changed, the same method is used as in the synchronization by table. Once we know that a table has been changed, to find out which records were changed, the hash of each record is calculated and compared with the corresponding hash that had been previously stored. Next, if the table was changed, its new hash is sent to the device just like in the synchronization by table. Also, 3 lists are sent, one for the new records, another for the records changed, and a third one for the records deleted. When the JSON arrives, the hash of each table is stored and its lists are processed in order. For the new records, an insert is made in the database, and if it fails due to a duplicate key, an update is made. For the records that have been changed, an update is made, and if there are no records, an insert is performed to insert them. A delete is run for the records deleted. A problem that is automatically solved by the synchronization process is the conflict caused by the numbering of auto-numbered keys. Auto-numbered keys are those keys set as auto-number, as well as keys numbered through a procedure or a transaction rule. For example, event day has a country and a speaker transaction, where both primary keys are auto-numbered. In addition, the country ID attribute is a foreign key of the speaker transaction. Suppose that the application is installed on 2 different devices, and it's working offline. From device 1, the country Uruguay is inserted with ID equals 1, and Brazil is inserted with ID equals 2. And from device 2, the country Argentina is inserted with ID equals 1, and Paraguay is inserted with ID equals 2. All the data is saved in the local database of each device. Once an internet connection is obtained, one of the devices is synchronized with the server, sending all the operations made through a business component over the local database. When the second device tries to synchronize, a conflict occurs because the country key stored in the server is repeated. Since auto-numbered keys are used, GeneXus solves the conflict in the server itself. This information is then returned to the device to have it make the same change locally in order to be consistent with the data on the server. Let's see how this can be done. GeneXus generates a new key for the repeated countries and updates the data on the server table with this newly generated ID. Next, it updates the speakers table so that the foreign keys match. Lastly, it updates the data on the device. In order to apply the changes made to the keys in the server, its response includes the matching of the values sent by the device and the values used to save the data in the server database. With this information, the device updates the keys in the local tables so that they're consistent with the server. The only synchronization conflicts that are automatically solved are those related to auto-numbered keys. In any other conflict, The device data is replaced with the server data. One way to minimize the conflicts caused by duplicate keys is using a unique identifier. A GUID, Global Unique Identifier, is an identifier generated in a pseudo-random way. Even though it cannot be guaranteed that this number is unique, there is an incredibly low probability that this number will be generated twice. In GeneXus, we have a GUID data type to assign to an identifier. With the auto-generate GUID property, we can have it automatically generated. In addition, methods and functions are available to operate with this data type. Its use is recommended in distributed execution environments, such as in smart device applications, where each user can enter data from his or her device. In the event that the receive and send operations are performed manually, the Synchronization API must be used to this end. This API is not included in the Smart Devices API folder. Instead, it's part of the grammar. It has the send and receive methods for synchronization, server status to determine the server status, and reset offline database to return the local database to its initial status, whether by running a create database operation to empty the tables or by using a preloaded database. With manual synchronization, for example, a panel for smart devices can be created to program the send and receive operations as shown in the image.